Hello everyone, my name is Akashdeep and in this presentation I will be discussing about 3D quantum Hall effect, which was shown in 2019 in a paper published in Nature. So let's start with the core of the quantum Hall effect. Quantum Hall effect was first seen in 1980s by Professor von Klitzing, where in two-dimensional electron gas system at very low temperature and strong magnetic field, we observed that the longitudinal conductivity vanishes and sigma xy, which is the transverse conductivity, only takes the quantized value, which is nu e square by h, where nu is the Landau filling factor. The quantum Hall effect in two dimensions can be well visualized through this plot of rho xx, which is the longitudinal resistivity, and rho xy, which is the transverse resistivity. So the blue curve, which is transverse resistivity, is linearly increasing in the low magnetic field regime, and when we further increase the magnetic field, we see a further step like structure here. As you could see, the rho xy almost remains constant for particular window of magnetic field and suddenly increases and jumps to the another plateau. So this is the characteristic of the quantum Hall effect, but we should also see rho xx, which is almost zero everywhere, and the peak of rho xx exists only at the point where the transition is happening from one plateau to another. As you could see, when we move from Landau filling factor 2 to 1, we are seeing a plateau in rho xx as well. So these characteristics of quantum Hall effect, this paper aims to show in three-dimensional system as well. So let's discuss about the challenges that not up till 2019 we were not able to experimentally demonstrate the quantum Hall effect in 3 dimensions. It was because mostly the system which were earlier tried upon, which also provided kind of a similar results, were quasi 2D systems. The quasi 2D systems are just 2D layers which are stacked one over each other to give the impression of 3D, but in reality they are actually still a 2D system. But how do you differentiate the quasi 2D system from 3D system? They could be distinguished by Fermi space topology, where quasi 2D systems have open Fermi wave vector in one direction, which is the stacking direction, and in 3D systems the Fermi wave vector are closed in all 3 directions. So this paper would be giving arguments that the quantum Hall effects phenomena which is arising, it's due to the 3-dimensionality of the system and not because of the 2D or quasi 2D system. So let's start with the setup used here. We take zirconium pentatelluride crystals, ZrTe5 crystals, which are orthorhombic layered, and in order to do the measurements, we take the standard Hall bar geometry where current is flowing in the x direction and the magnetic field could be in the z direction. One thing also which should also be noticed, that the ZrTe5 crystals show 2 types of carriers, electron carriers and the hole carriers. The electron carriers dominate at the low temperature and the hole carriers dominate at the higher temperature. We are mostly dealing with this regime where in low temperature regime, where we have a small density of electrons, but they have very high mobility. So this is one of the reasons why we are taking this sample, because it provides very high mobility of electrons at the very low temperature. So we mostly our measurements would be based around this temperature range. So let's start with the measurements of rho xx with respect to the magnetic field. As you could very well see, when the magnetic field is pointed in the 3 different principal directions, x, y and z, we see the oscillation in the periodic oscillation in rho xx. These oscillations are known as Shubnikov-Diaz oscillations, and the presence of SDH oscillations in all 3 directions is the valid fact that the system is indeed 3-dimensional and not quasi 2D systems, because if the Fermi wave vector was if the Fermi wave vector was open in any of the direction, we would have not observed SDH oscillations in all 3 directions. Hence, this is the good motivating factor that okay, our sample is indeed a 3D sample. So we also do the metal insulator measurements related to the metal insulator transition in the sample, where it could be very well seen that the rho xx versus t graph shows increasing nature below a certain critical magnetic field, and above that it shows the reverse trend. The rho xx decreases with increase in temperature. This could suggest that below this critical magnetic field our sample behaves like a metal, and above that it behaves like an insulator. Let's talk about the measurements of rho xx and rho xy with respect to magnetic field. So the purple curve, which is the rho xy, has increasing nature when we increase the magnetic field, as you could see, and the presence of plateaus can also be fairly evident here. So you could see the first it rises and kind of reaches the plateau, and again it rises and reaches a plateau. And rho xx also show a oscillatory nature with the peaks coinciding with the transition where rho xx transitions from one peak to another peak. So you could see here rho xx is well positioned where where plateaus are changing, this plateau to this plateau. Hence, these are the characteristics of quantum Hall effect in 3 dimensions. One thing that should also be noticed that rho xx vanishes only in this window around magnetic field of 2 Teslas, and at the same time where rho xx vanishes, we have a high value of rho xy as well. So putting this along with the other characteristics, for example, the peaks coinciding and the presence of plateaus, this gives the complete picture of quantum Hall effect in 3 dimensions. But is it really in 3 dimensions? That we have to check. So we give the following arguments to prove that this is indeed a 3D phenomena. The first argument is the STS oscillations are present in all directions with distinctive frequencies. So that means that the Fermi wave vector is closed in all 3 directions, indicative of the 3D substance. The another argument which we give is when we calculate the Hall resistivity, which is rho xy upon d, where d is the width of the sample, on the plateau where nu equals to 1, we are talking about this area, this region where Landau filling factor equals to 1, the Hall resistivity comes out to be 1.35 ohm. So this quanta of resistance, when we compare with the Klitzing constant, which is h by e square, which is 25 kilo ohm, we could very well see here Klitzing constant has a very large value compared to the Hall resistivity which we are measuring here. That simply suggests that the quantum Hall effect in this sample is because of the 3-dimensionality of the system and arising from the bulk of it. Another argument which could be given here is that the system bandwidth was found to be 400 mega electron volts, which is much greater than the Landau spacing of 25 mega electron volts. So these possible explanations point to the direction where we could conclusively say that this is indeed a 3D phenomena. We give our conclusion and results here. Rho xx approaches 0 with respect to magnetic field around 1.7 to 2.2 Tesla only. We could see here it's only this window of magnetic field we see the vanishing rho xx and high value of rho xy, not anywhere else. We also see Shruvnikov-de Haas oscillations in rho xx with the peak coinciding with the change of the plateaus of rho xy owing to the change in the Landau number. The plateaus of rho xy survive up to the temperature of 15 Kelvin. And on the other hand, we also show the presence of metal, hole electron type metal and hole type insulating transition, which is driven by the critical magnetic field. So this seminal work could be the landmark in first of all demonstrating the 3-dimensional quantum Hall effect and also opening up the new dimensions for the theoretical aspect, which could provide the possible explanation that why this phenomena is existing in 3 dimensions and how it works. So these are the references attached. This Fang et al. Is the latest paper published in 2019, on which this presentation is based upon. And thank you for watching this video.